Okay, so we are going to look at a practice problem using angular momentum and angular impulse. And this problem reads, a majorette, who is someone who twirls a baton, is holding her baton straight out with one hand, such that the baton is hanging straight down. So there's my picture. The baton has a mass of 0.6 kilograms and a length of 0.75 meters. Now with her other hand, she hits that baton with 900 newtons of force, and she makes that contact for 0.03 seconds. The question is, what is the angular speed of that baton immediately after she hits it? All right. Now, a thin rod rotating about one end has a rotational inertia of 1/3 the mass times the length squared. And so given the mass and the radius of the or length of the baton, we know that that rotational inertia is 0.1125 kilograms times meters squared. So we want to use angular momentum and impulse to solve this problem. Now, we know that an impulse is a change in the angular momentum, and an impulse force over that time that force is applied causes that impulse. And so we know that the impulse, which is equal to our change in angular momentum, is equal to the torque times the time over which that torque is applied. I think I said force last time. That's our linear impulse. This is our rotational impulse. So our change in momentum, well, that's the final momentum, angular momentum, we're talking about angular, times the initial, or minus the initial angular momentum, is equal to the torque times the time over which that torque is applied. Our final angular momentum is I omega final. So the moment of inertia times the angular speed, minus our initial angular momentum, I times omega initial, is again equal to the torque times the time. Well, we know that this baton is starting out not moving, not rotating, and so the initial angular speed is 0. And we're left with I times omega final is equal to the torque times the time. And since I want omega final, I can solve for omega final. Now, I'm given the time that torque happens over 0.003 seconds, so 3 milliseconds. And I know the moment of inertia for my object, but I don't know the torque. So if I need to solve for the torque, I need to do a torque analysis. So we do that by first drawing an extended free body diagram. So here's my baton. Now we know that there is the force of the hand holding the baton. That's going to have some vertical component and some horizontal component. And I don't know what those are, and I can make good guesses at that direction, but I don't really even know the direction perhaps either, and that's okay. You can put them in their components. You can always make it positive, and if you have to solve for it, it'll tell you whether it's positive or negative in the solution, but it's also good to try to make a good educated guess at the beginning as well. All right, why did I do it this way? Well, I know that the force of gravity is acting down on this object, and that acts at the geometric center for a uniformly distributed object, and we're going to make the assumption that this baton is, given the information that we've been provided, or I should say lack of, if not told. That's not a bad assumption to make in most cases. And if it's acting down, then the force of the hand is probably holding it up. I also know that there's a force acting, as I've drawn it, to the right. This is the force of the hit. All right, so, and it acts also at the center and perfectly perpendicular given the problem. So, as we continue our torque analysis, we have to define where are we going to set the rotation, the pivot point. And I'm going to put it at the hand because I don't know those forces. And therefore, the torque of the hand vertically and the torque of the hand horizontally are going to be 0. I'm at the pivot point, and so there's no radius, so those torques are 0. The torque of the force of gravity is also 0. How come? Well, this is acting along the line of the radius. There's no perpendicular component to that radius. Therefore, there's no torque exerted by the force of gravity. It's not going to rotate the object when it's hanging straight down like that. So the only torque acting is the torque of the hit. So that's going to be the force of the hit times the radius of the hit times the sine of the angle of the hit. And we know that that force we're given is 900 newtons. The radius is at the pivot, at the midpoint, so 0.375 meters, and it's acting perfectly perpendicular, and in this case, a positive 90 degrees. And so the torque generated by that hit is 337.5 Newton meters. So given that, I can now use that information to solve for my angular speed. So we have 337.5 times 0.003, all divided by 0.1125. And we find 337.5 times 0.003 divided by 0.1125. We have a final angular speed of 9 radians per second. All right, so using angular momentum and impulse to solve this problem of the rotating baton. Good job.